Good morning. It's a great pleasure to be here. I'm not part of the community. I'm the broader, community in networking and the systems, in the research arena. So it's a great pleasure to come here to talk about some of my work. This is a talk I had to put together. It was sort of I was talking to the chairs, saying it has, I need to really, thinking through what I'm going to talk about to a research audience. So I'm going to give it a try. I know, there's a Disneyland on the side, and there's competition for. You want me to be here? Okay, thank you. That's a visual cure. Okay, so I'm going to talk about three stories. One is the research before I founded Conviva. It's most in the internet space. And the second one is Conviva, which is a company I co-founded, and the business evolution and also the technology. And then obviously the point here is the entrepreneurship and research have some interplay, and hopefully I will weave that theme into this. Now, we're living a very interesting time. Well, every time is interesting. So when I was just started at graduate school at Berkeley, a senior graduate student, Kishoff, now he's a professor at Waterloo, and he asked this question. You see, if you were around 1500, where would you rather be? So, he was from India. I was from China at that time. We were both in Berkeley. And the answer he said, again, everybody has a different answer. He said Florence. Because that's where Michelangelo and Da Vinci were there. And that was the very amazing time of the Renaissance. Right? So again, you look at world history, I'm sure that other people will give different answers. Now, the reason he was asking the question is, we're in the early 90s. You can see I'm old. So a lot of young folks here. So what about in the 1990s? Interesting time. So I was at Berkeley, amazing time. So I was there, and when I was a student, at that time, Professor Richard Newton, the late Professor Richard Newton, he was a department head. He gave us a talk, and he was using transparencies, no PowerPoint, for those of you who remember. So, and he drew 4 dogs on the slides. And he asked all the graduate students, saying, what's the differences among the 4 dogs? And by the way, I cheated. I put some photos here. It's hard to tell, by the way. He was very good. The 4 dogs, they draw very, very similar, hand drawn. And we're saying, maybe the tail's a little bit different, maybe the eyes a little bit. No, he said, no, it's not that's not the thing he was trying to say. He said the first dog is different from all the other dogs. Because the first dog has a different view. They see an open field in front of you. And you have to make some decisions. And you can either lead to a bone, or you can run into a hole. So you have a different passion. You have different emotion. You have excitement and fear. Where the other dogs, no matter the second or the fourth, they see the same view, the rear end of the previous dog. So his, advice to all of us as a graduate student is, there's no second. There's no difference between the second dog and the 100th dog. You have to be the lead dog. So that was the motivation in terms of its research, its entrepreneurship, it's about innovation. Okay? So, now, go back. When we're living interesting time. That was the time I started at Berkeley. That time, if you can remember, internet was very, very small. But it's already pretty big at that time, have hundreds of thousands of hosts. But hundreds of thousands, not billions. And the internet backbone was running at 1.5 megabits per second. So that was the backbone of the entire US internet. So it was very interesting, but I was a grad student, I was looking for a topic. I was thinking about how to become a lead dog. And that was, a workshop happened that time. My Ph.D. advisor, Domenico Ferrari, and many other folks were there. It was a workshop. And they were talking about topics a little bit futuristic. They would say, what will be the future applications beyond telnet? Could be video. If it were for video, what does it mean for the network? So that was the question we asked when the internet access link was, dial-up speed. The backbone is 1.5 megabits per second. I think the point here is we should imagine about the future. Is the future will come? So I did my thesis on this topic. I was doing real-time internet protocol for video. I finished in 93. 93 was a very, very special year for me. But actually, for the rest of the world, it's also very, very special. Because that was when, what? 1993. Mosaic was released. That was the beginning of the web. Because I was at Berkeley, and there was a talk on Mosaic, and all system people look at this, well, it is a glorified FTP program with a GUI. Didn't quite appreciate the significance of HTTP protocol in the web. This is where, again, it was not invented by computer scientists, by the way. Right? This is what, it's an application by physicists. They build an application they need to use, access to information. And so this is an example of entrepreneurship, that you take a technology, make it accessible, make it easier, and then eventually Netscape, Andreessen, and all of a sudden, the world took off. The internet took off. And this is sort of the exponential growth, the doubling, the size of the internet doubling every 9 months. Mostly driven by the web adoption, not video. But, again, not fully, appreciate the trend. We're still, again, a lot of iconic names, companies. Okay, I couldn't see. Okay, now lots of companies there. Hotmail. Anybody still have a Hotmail email? Yes. Well, see, this is your sort of you're showing how old you are. That's but some of the other companies are still here. Google, Amazon, among the most valuable companies today. They're cloud companies now. But they started off that time, it's an application on top of the internet. Now, there are other, because I was working on video, internet video, there are lots of technologies at that time, and but didn't quite take off yet. So you couldn't predict the future. You're trying to invent the future. It's part of the pioneer. So we said, well, what could be the reason? Well, the internet doesn't support quality of service. It doesn't support multicast. So not just me, there's a whole community working on this. Huge amount of research effort. I remember I was interviewing at Berkeley, at CMU, and Satya was asking me, Hui, do you really think you want to put this sophisticated mechanism inside the network? I said, yes. He still offered me a job. I went there, but none of them were actually adopted. But I was doing the research ahead of myself. I work on scheduling algorithms. I work on, Jiang. We talk about Jiang's thesis, got the ACM Dissertation Award. He was working on this also, because we're working on this together. And it was very interesting research, but ultimately, it was a wrong diagnosis. The video wasn't taking off, because variety of reasons. ultimately, it was because ecosystem wasn't ready. Software wasn't ready, encoder wasn't ready, network broadband penetration wasn't there. Many, many reasons it wasn't there. And then, if you think about this, again, with the benefit of hindsight, you say whether it is web internet or the QE internet, the web internet took off, was driven by the killer apps. And they will continue to drive. There's no room, there's no appetite to change the underlying infrastructure. It's working, the applications are taking off. Many of the research projects, even though they're very, very interesting, and did not really get adopted. So an interesting lesson for me, doing research, and the next set of projects I was working on, one is called the 4D project, the other called the N-System Multicast project. Here, the focus is on saying where really the innovation can happen, can really drive rapid iteration, drive rapid adoption. If you look at the infrastructure, the data plane, the switches and routers, very, very difficult. When I was working on scheduling algorithms, I have to build in the chips. Now, and then they have to put in routers. And they have to be deployed out there. That's a 10-year deployment cycle. In the age of doubling every 9 months, that's a century. So those ideas are harder to get deployed because new requirements are changing so fast. However, a software layer decoupled from the switches, that can be deployed much faster. The other thing that we notice is, look, the endpoints evolving applications can do a lot more things. You can put servers inside the network. You can use them to build distributed services. At that time, it was a novel concept, right? You have host talking to a host. There's file system servers, right, in local range. But from the global services, global internet services, it's really connectivity services. There's no computation services or storage services. But if we can deploy those services on the servers or client machines, it'll be faster. It could be internet-wide services. So those are the projects that I've been working on. I think that, again, the theme here is have control plane innovation instead of data plane. Innovate on the upper layer of the stack instead of lower level of the stack. Because that can, and you can do a lot of things with them. Potential overcome many of the performance challenges. If you can overcome them, it can be adopted. So, one project I work on called N-System Multicast. Basically, we're using multicast instead of using the switches to support multicast. We use endpoint to forward packets. Do a self-organizing tree. Or a mesh. So we did we built the system. SIGCOMM happened to happen the year 2002 at Pittsburgh. We say, well, we need to. And another amazing event happened there is RoboCop. It was the first RoboCop. And I was talking to our CMU folks here. Peter Stone. He did the thesis RoboCop. He was sitting next to me. He's an amazing soccer player. And he did his thesis on RoboSoccer. And by the way, he just got the ACM, sort of award, Island New World Research Award for AI, 2 weeks ago, for his work in all this work, at the very beginning of RoboCop. But that time it's crazy, have robots playing soccer is a very novel idea. But then they were organized the first tournament, and we say, well, why don't we webcast to the whole world? But then that time the technologies require you have IP multicast. And it's, actually they built an overlay network called Mbone to do the IP multicast. But again, it's very, very difficult to set it up. So we say, why don't we use this N-System Multicast? You can just download a piece of software, and then you can watch the RoboCop. It turned out to be working really, really well. We set up the system, hundreds of participants at that time is considered to be big, tuning in from the world, watching the RoboCop. So what's the lesson we learned? It could work. It can be fast adopted. So it proven the thesis that services can be done this way. Now, obviously, from that point on, there are lots of other industry activities. Skype, if you remember, was a telephony system built on top of the internet, right? It was, at that time, was considered to be, for those of us working on doing QoS inside the network, was saying, can you really do this? That was before, the Zoom. Skype was the system. Yes, it could be done at the endpoint. Lots of things can be done on the endpoint. So it's a very, very interesting observation. So, again, I was working on streaming, but then the streaming finally happened. What was the signature event? Year 2005. YouTube. YouTube was founded. In the first year, had 100 million streams. 100 million. That's a lot of video. But do you know how much YouTube's serving today? Several billions per day. But that time, it was a pioneer. And then, for those of you who are following sports, March Madness was webcast over the internet for the first time. And then we have the, the concert, the AIDS concert for global awareness for, they got webcasts over the internet. And we have the iPod that time, again, actually, people listening, watching video on the mobile devices, not on the iPhone first, it's on iPod. So those are some of the key signals. All of a sudden, it took off. So we thought, we've been working on this for so long. We're infrastructure people, we're technology people. We want to set up a company to support the high quality video distribution over the internet. So that's when we first started. It's called Renera. Jiang, Stoica, and I co-founded the company. And that was so you're the first time you've seen it. This is a slide, and people haven't seen this for a long time other than the VCs. Now, what is the problem statement? What is the problem we're trying to solve? We're saying we want to distribute high quality video distribution over the internet, but we're not controlling the AT&T networks, we're not controlling the encoders, we're not controlling the servers. Still, it's possible to control high quality, provide high quality for the video. If you only control the endpoint, what kind of techniques we can employ to improve the quality of the video? There are really three big ideas. One is we should optimize what I call qualitative experience metrics. This is where I don't want to have a buffering. I want a high bit rates. I want, when you click video, it show up quickly. Notice these are not packet loss rate. This is not CPU utilization. This is not memory utilization. Those are lower level performance metrics, right? And we want to optimize the application level quality experience. The second is, once we think about that, we say, where do you have access of that? It is at the screen. It is where the human eyes watch the video. You want to be as close as possible to that human eyes. That's on the screen. Now, nowadays, we can put a sensor into your brain, right? Because it's really about satisfying humans' need to understand what the quality of service is. And the second is we can really measure. We should measure continuously. We should measure every stream. We should measure on every second. That's the second idea. The third one is, well, after you measure it, what do you do? Well, you send them to a centralized control plane, and you do a lot of analytics, you do a lot of AI, and then you generate optimization algorithms. trying to help to improve the video. So 2 big ideas, right? One is endpoint, application upper layer. The other was, control plane, which are 2 projects which I was involved with. So, computing and optimize quality metrics. Again, I won't go into all of this. There's, we can read a lot of papers. We did write a lot of papers, and this can be extremely sophisticated, and it cannot be really done by the CDNs. At that time, it was, why don't we do this in the CDNs? Well, CDNs talking about the packet loss rate, talking about, sort of the start time of when you first click, when the first byte arrives. You really want to go all the way to the application level. So that's the first. I'll just click through this. As I said, it can be tremendous sophistication here. Now, this one is, you probably can not see much. It basically says, once we do every stream, now I can say, well, how many of them on this CDN? How many is from the geo region? How many of them in different device types? I can do tremendous analysis on this and really find lots of interesting information. So, and those information will be found in this, what I call the internet scale control plane. Here, information is sent in real time to this centralized control plane. But what is it? It's a cluster of machines. What does it do? Well, this is nowadays we call it cloud. That's a private cloud. The private cloud is going to real-time process all those information and trying to make some, algorithm decisions. I'll give you some examples. Here's an example, right? If we have some buffering events happening, now, as I said, because I have all the information in the world, then I can do dimensional analysis, right? And then there could be several reasons. Depending what the reasons are, it could either be the network's congested, or some subset of network, sort of the peering point is congested, or it could be a CDN has a problem. Depending what those reasons are, you will take very different control actions. So that's the kind of analysis we can do when you have this full census QE measurements. And depending also what performance metrics you want to optimize for, you will take different control actions. Again, they are very application specific. That's why you want to do it in the application level. Outside the network. I'm a network person. I say, well, outside the switches, do not want to talk to Cisco, do not want to talk to AT&T, do not want to talk to Akamai. Right? How can you do this without talking to them? So we did this. You can see tremendous benefit, and this is just an example. Early days, we launched with a customer. We can see that average bit rate increased, buffering ratio decreased. Higher resolution, less spinning wheels. So we have since deployed many of the leading brands. We process, lots of data, trillions of events per day, deployed in many, many endpoints, billions of sensors, SDKs deployed on each of the endpoint devices. So a huge amount of data we can gather and process. So let me go under the hood a little bit. So how do you process this? Right? It's a lot of data. Now this is where we went to the analytics space. We went to how do we really process large amount of data? Now, the first thing, as I said, there's lots of, let's see, I'm trying to synchronize. Okay, good. Lots of metrics. I will not bore you on this. I gave you some examples. Let's dive into one example. Here's an example. Again, all of those we come up with our definitions. We did our study, and then eventually customer wants us to do more. This is an example. It's a nuanced metrics called connection induced rebuffering pattern. So what does it mean? Buffering is, well, a player was a playing state, a buffering state. So on that. But here, the customer want to understand is, if I start a new connection, how bad is the buffering? Compared to what? While I'm continue playing, buffering events will also happen, right? You want to know at the beginning of the session how bad the buffering is. Now, what do you get? What's the input? The input is a lot of those events, right? You have, buffer is empty, buffer state is playing, you have a seek, you have pause, and then I change my bit rates, and then I move to a different CDN. Those are the inputs. Based on all those inputs, you need to compute some metrics. This is a very interesting algorithm problem. It's a very interesting system problem. So there's how do you compute it? Now the challenge here again is I'm trying to synchronize between those two screens. There are many, many devices video can be played on. Could be game consoles, smart TVs, mobile phones, pads, and PCs, right? Many of them. It's worse than that. They all have different versions. They have different software versions. They have their OS versions, right? And you have all sort of metrics out there. So ultimately, it's a tutorial problem. You have too many of them. So there's also engineering and architecture decision. Beyond the way, if an algorithm, you can compute them. Now, where do you compute them? So we made a decision, we should compute it in the cloud. And at that time, most of the state-of-the-art systems, even today, they computed in the devices. Why compute it in the devices? Well, because it's more scalable, right? You have billions of devices out there. It does its own computation. It already has power, has memory. It's easy to do it there. However, it's very difficult to maintain consistency, very difficult to upgrade, right? All the trade-off between on-prem software versus cloud software apply to here, right? If you were to move to the cloud, it has many, many benefits, except you have to pay the cost, because I own the cloud, right? It has to be very easy and efficient. And in real time, I have to compute. Just take time to compute. I'll give you an example, sort of, I'm just gonna be very, very fast to go through this. If you think about this, if you're, early days Conviva engineers think about this, and what do we think? It's a table. We collect all the events and put them in a table. This is the whole world is a tabular model, right? The whole databases, all the structured data are in the tables. You can put them in the table, and then now it matters, this is a time series, database. And then you need to figure out a variety of steps to do it. But we have to do very unnatural things because that wasn't what a tabular system was designed for. We have to figure out, we have to scan both on the column and rows. So I'm not going to run this algorithm. This is in itself a very interesting talk for people who really care about algorithms. Because the database, the tabular data structure are really optimized for two fundamental metrics. One is aggregation, operation, sorry. One is a filter. I can select a set of rows, or I can add them up. That's aggregation, right? But that's not what we're trying to do, because we're trying to build a state machine. We want to track certain state, and want to compute certain metrics we call the stateful metrics. Well, that's very hard. I'm just going to go through this animation. This all saying a different way to say it's hard. And here, you can do it, by the way. And this is the code. This is the code we wrote. And it did it. Now we have to parallelize it, right? You have to run on multiple machines. It's like programming now. SIGCOMM is the highest level form of programming paradigm. And we're not, but it feels like we're programming in assembly language. Why? Because the abstraction is wrong. This is the wrong abstraction for this type of computation. Now, when we started out, state-of-art distributed system that time, Google just did MapReduce, amazing. Hadoop, open source. So we implement first on Hadoop. It was too slow, batch processing. It forced us to think about alternative paradigms. Jiang and his students at Berkeley built Spark. Matei, Jiang, and the rest of the team. And we're our contribution is the motivation. Our contribution is early users of Spark. It's a big step forward. And still not good enough. Why? It's a tabular abstraction. Spark first has RDD, eventually has Spark SQL. It's a SQL. So we have to invent another paradigm, which I call the time-state analytics. Now, this is the first and only paper I published in a database conference. So we wrote we have to build this, and we went to the database community. We say, well, for this type of workload, SQL is terrible. We need to do something different. Well, I walk out live. They were very skeptical. They love SQL. That's attacking their Bibles, right? Their religion. But they understand. So everybody come up with their own tricks. They say, no, what if you do this? What if you do that? The reality is none of them are good. Again, you can use assembly language to do anything. It's just very complicated, error-prone. So I think the key word here is continuous and stateful, right? We continue to track a state machine, and we want to compute stateful metrics, patterns. So the way we should think about this, introducing a new abstraction layer, we call them timeline. And the timeline is built on top of the SQL. And then you can really optimize. Like when you introduce the interlayer abstraction, first is simplify the programming. The next one is actually you can do tremendous optimization, just like a SQL database, that you can do tremendous optimization once. Just because the SQL code is there doesn't mean the query plan is the same. You write the SQL. Same thing here. Once you have the abstraction, you can have the compiler, the query engines to really optimize the runtime. Same idea here. This shows the code can be simpler. This shows the performance can be significantly higher. Now, it happened to be the timeline abstraction. This we implement, obviously, early on in a CPU. If you run a GPU, it can be even much more powerful because this type of abstraction is much easier to run in a GPU environment. Now, I'm completing the architecture piece, saying really 4 big things, right, for this type of systems. And these systems is what we're trying to do. We're trying to do data-driven performance optimization for internet scale applications or services. Video streaming is one of them, right? And in order to do this, we have this architecture has 4 measuring the application level metrics. Video is called QoE. Measure continuously, measure all the time, measure every interactions, every stream. And then you send them to a centralized processing unit. You do look at the performance at aggregate level globally. Now you need a very, very important, you need a very powerful engine to do this. And time state is that powerful engine. So I'm just gonna talk through a little bit, I'm trying to stick with time. So I'm gonna talk through a couple other use cases. Internet scale services. What others? Well, there are many, many. Well, first of all, it's not just a string of apps. We're living in a world that every services are digital services, right? And nowadays, you buy stuff online. You book an airline online, right? Everything. So those apps are very sophisticated applications. And they fail all the time. The performance are not as good. I don't know, just you, just me, but there are lots of frustrations with those powerful softwares. We know softwares are very, very faulty. You can do the same thing. I'll give you an example. This is an example to show what things you can really happens behind the scene. You go to an e-commerce site, there's a lot of things happening. A lot of actions are happening. So, as I said, it's a very sophisticated software. Okay? Multiple steps. And if you look at the behind the scenes, a lot of API calls to both its own services and third-party services. Now, you want to do analysis of this. You want to figure out where the errors are, very similarly like what we've done, for the video. And you can. The same architecture applies. You can do this. What type of analysis you want to do? You want to talk about, when the search performance works, how the checkout process works, how the login process works, how the entire, from the user come in to when you click a buy, how that process works, how much friction is there. So all of those, abstractly, is a stateful computation problem. Here's one example, recent customer example. We notice that between two different type of browser versions, the users have a very different conversion rate. Right? Conversion meaning, did you finish the buying process? Right? Conversion impact your conversion rate. It should be a human behavior. Right? It turns out, you go to ChatGPT, you ask what those browser versions mean. One is with privacy setting, the other is without. So it's actually very interesting to tell you the users with privacy setting actually are easier to convert. It's very interesting. It's a human behavior that you will never know had you not have this comprehensive data set. It's an example of that. Okay? Now, going forward, we're in the world of AI. We're in the world of agent. If you're following all the hypes today, the web is going to the next web, right? The agentic web, the next big leap. The agents will help to mediate, absorb many of the functionalities of human being, operated for human behalf to interact with the rest of the system, right? And Benioff of the Salesforce, again, he's a very big thinker, sometimes overshoot a little bit, but he said for this year, his company's goal is to put 1 billion agents out there, 2025. So we're in another phase of internet evolution. That just means, what is the agent, again, abstractly? Let's start with the use cases. These are, obviously we know coding is a great co-pilot for us. But really, some of the use cases I'm talking about here is someone helping to do shopping. Someone helping to do, if you're a salesperson, now the people here are a salesperson, but you get on the phone, you call someone. Let's say you get on the phone, you call, I want to apply to CMU. I'm selling. Student's a seller. Now, when I'm talking to some Professor Satya, then the agent should pop out all the Satya's papers. And Satya was asking something, what about this work I done, internet suspended resume? Well, the agent will immediately go to the web, find a paper, tell me what my talking points are, and I can answer intelligence to that. That's the agent we're talking about. And those are already being deployed commercially. Right? Obviously, you talk to on the phone to some person for customer support, there's another computer is talking to you back. That's a customer support agent. Now, there's both autonomous mode, always, or there's a co-pilot mode, right? Those are some of the agents. Now, go back to my stack version, where the geeks, we're thinking about software. It's another application layer more than your web servers, right? This is a higher level, at the upper level of the stack. In fact, now it's absorbed some of the human logic. That's the agent. Now, what's the issue with the agent? Well, agent talks to a large language model. That means what? They can hallucinate. Agents talk to each other through natural language type of protocols, MCP. Those protocols are very powerful, but much more ambiguous. That means what? The whole system is much more ambiguous and has a lot of potential performance and accuracy problems. So this is sort of some of the architecture, the diagram, if you put a diagram there. But if you really want to really understand the system, you need monitoring, not beyond just the application, but you need to also monitor the agent. Because why? Because the agent now taking some of the application logic, right? Human logic in it. You need to go through the entire session. You think about the buying session I just showed you. It's a stateful process. I want to know step by step how it works, and also go through the multiple steps. So this is another very interesting use case, is for agent performance. In fact, it requires even more powerful time-state analytics because of the more type of entities. And as I mentioned, the user interaction, user's intention is a lot more ambiguous, but also richer, right? The protocols among agents, much more powerful, but also ambiguous. So where do you do this? You can say how agents runs, how many tokens it can process every day or every second, what's the tokens rate you can process. That's one type of performance. But really what you care about is the outcome. Does it really finish the tasks to a satisfaction level? Satisfaction to whom? To a human being. How do you know it satisfies a human being's outcome? It's hard to infer that. However, it could be if you really deeply understand this from the entire journey perspective, and also at scale. The more you look at those agent performances, both spatially and temporally, more understanding you can gain in terms of whether a user outcome gets satisfied. I'm just giving an example, but I would, in the interest of time, I'm going to skip this. I'm going to try to slow down a little bit because I'm trying to wrap this up and hopefully leave some time for discussion. First of all, as researchers, it's a very humbling experience. Many of the ideas do not pan out. It's intended. I want to add this word, a very subtle word, intended, because you have an idea, you have very specific use case scenarios, and you want to do it, it may not pan out. But it could pan out in some other ways, right? But partially, as I said, if you're the lead dog, you want to be the lead dog, sometimes you're going to fall into a ditch. Let's go with the territory. So I think we should, again, this emotional stability that you need to have courage, you need not be fear, those things are important whether it's an entrepreneur or as a researcher. some of the projects did not quite pan out. But the other projects, but you never know. Sometimes things pan out in unexpected ways. For example, I did a lot of work on scheduling algorithms. They're not in the networks, but now they're in the cloud, right? Did not predict the emergence of cloud, but now they're really put there. Now, if you look at the control plane work we've done, the first deployment is not actually in the video I'm talking about. It's actually inside the data center networks. This is where the software-defined networks. If you look at the Google network, right, not on both the local and global networks, they're using a control plane to manage the entire system. They're not the traditional routing protocols anymore, right? And if you look at all the distributed services in the cloud, there's always a component called a coordinator or orchestrator. That's the control plane component. It's not a fully distributed, right? Our purists in distributed systems always say, well, everything is sort of fully distributed. But this hierarchy of a control and other computation nodes become a prevalent pattern, right? MapReduce, same thing. So this idea is a very powerful idea. It manifests in multiple places. Peer-to-peer, we're doing peer-to-peer streaming. And one of my students who were on the project, Yang Hua, he actually proposed at Pittsburgh at that time, saying we shouldn't do peer-to-peer streaming. We should match the drivers with the passengers. That was a good idea. Well, none of us, just like we did not appreciate the web and HTTP, we all said, well, this is impossible. We cannot solve the trust problem. Very interestingly, the founder of Uber founded a company before Uber called RedSwoosh. Nobody remember that, because I remember it. It was my competitor. It does peer-to-peer streaming, eventually acquired by Akamai. But he had the courage to found a company called Uber, and it became so much more successful. So this concept of peer-to-peer is there, right? Even the peer-to-peer streaming didn't pan out. And the concept of overlay networks, even more powerful. I think that obviously the emergence of distributed servers providing global internet services, starting with Akamai. Akamai was an overlay network. Akamai would say they were the first cloud companies, but then the computation, storage inside the networks, providing, again, on top of the internet, but providing network-wide services. That's the cloud today. Very powerful concepts. Now, I also want to talk a little bit about, sort of search. And we've been working very, very closely, at Conviva. Obviously, Conviva's origin was many of the research projects. But during the Conviva's evolution, we have encountered many, many problems. We exposed many problems, and many researchers come in to help us. And they've done amazing research. Junchen Jiang, he's in Chicago. He did a thesis to how to do automatic alerting, the data we have. That's got the CMU's Dissertation Award. We study how we predict humans' attention. I'm going to come back to this word, attention, from the QE parameters. So that's a SIGCOMM paper we got, recently, was get a SIGCOMM paper award. Very, very interesting. Probably the most successful, incubated technology was Spark. Amazingly successful. So there is two sides. One is we saw the success. Second, we didn't capitalize on it within Conviva, but Jiang did. It eventually become Databricks. But the problem was motivated by this type of workload, right? Now we said even Spark was not good enough for the kind of workload we talk about. So we had to invent time-state analytics. So you go to the real world, you create a new own reality. The reality gave you back new set of problems you could never imagine. right? And motivate the next set of research and start that cycle again. So it's very, very interesting. I mentioned this in terms of architecture pattern. I think this is a very powerful architecture pattern. I think it was, we're pursuing this. I think that many, many scenarios, this will be applicable. I'll talk a little bit about our own journey. We started from the business perspective. Actually, our product continued to iterate. We start out as a peer-to-peer delivery. It didn't pan out. We're multi-CDN optimization. That's not our primary business either. And we can all talk about it. Ultimately, analytics, the people's need to really understand what's going on, so much more powerful. It's very interesting. And it's basically a co-pilot for human being to do many things. So that's actually is the business. And this is a very powerful business. The whole companies are created, the whole industry are created to do this. If you look at what Tableau, what do they call themselves? They call it an analytics company. It's a UI for analytics. You look at Snowflake, Databricks, what they call themselves. They also call themselves data platform and analytics companies. Because what's the usage of those data for analytics? So Conviva is pursuing a different type of analytics for operational data. Right? The operational data is from the machine. It's time events data. It's not only your sales forecast, only your your marketing information. It has 1,000 times more information and coming in real time, and you need to make real-time decisions on that. So that's the kind of space we're in. Now, it took us some time to find what is the business, what is really the differentiated technologies, the moat. But if you look at, you want to find time, you need to have a little bit of patience. Obviously, AI is the word. I was at the ACM banquet like 2 weeks ago, and the chair said, let me try to avoid the word AI. You couldn't, you cannot, because the award winners is the AI winner. But if you look at neural net, right, it was such a cold, problem space. People did not really pay attention. And there's some persistence. You need to really sustain that, is a lack of attention, if I call it. Nobody pay attention to what you do, right? Till it breaks through, right? And I think I was at the Turing Award banquet, and it was on reinforcement learning, right? Andrew Button and Richard Sutton. And the person was asking them, it's an interview, saying, how do you continue the work you were doing when nobody cares what you do? And Richard Sutton says, well, actually, I enjoyed it. And he said, you don't have to just follow the fashion. And then Andrew Button says, pursue the passion is very important. So this is both apply to definitely for research, but even you look at the AI, because given we talk about, AI as a word, NVIDIA is the most powerful company today. But NVIDIA's history, right? They built a chip looking for application, right? Graphics, gaming, Bitcoin, AI, right? It took a long time before it really hit the stride, right? So time is a very interesting factor in all of those work we're doing. Lots of young researchers here. Hopefully, your work will be very successful in 5 years, but don't get discouraged if it's not 5 years, or it's not 5 months. I think the other thing about common for research and entrepreneurship is you got to work with amazing people. This is not an individual sport, it's a team sport. And so I had the privilege to work and the pleasure of working with many, many great people. It's a part of the professional journey, but definitely, lots of learning. let me conclude, because it was hard to conclude a talk, and I'm using two of my role models, to conclude the talk. Now, all of us, many spent time at Carnegie Mellon, understand the impact Herb Simon made to all of us and to the field, right? And we use this, I use this in history talk, because we talk about attention and experience. We say we want to optimize user experience. The user experience is attention. And this is the scarcest resource. It's your time spending here, right? You could spend time here, or you could go to Disneyland. Right? Attention is hard. And then whether it's a video, it's an app, or it's human being interactions, you want to keep people's attention. The second thing is very important, is the trust. Now we're in the AI world, we're talking about AI pioneer, right? Talking about trust. And this trust is not beyond just a security trust. It's a fundamental human emotional trust, right? Can we trust AI? Can you trust your friend? That's this trust is about, right? How do you develop a trust for AI? It's very, very, sort of interesting time to revisit. The last but not least, I'll close with the amazing Steve Jobs, right? So whether, started with Richard Newton, we want to be the lead dog. The lead dog need to stay hungry and stay foolish, because you never know where you're going. You just need to keep on going. Thank you very much.
Thank you very much, Hui, for the inspiring and wonderful talk. We have time for a couple of questions.
It's Varun Kumar from CMU. I wanted to ask you about how you'd advise students. So my students always ask me, what's going to be the next big thing? In 1990s, you had the foresight to imagine that video streaming is the best thing, enough to invest in your entire thesis, and then see it really happen, commercialize 15 years later. So if you had to talk to someone today, working on what would be the next big thing in 2035, 2040, what would that be for the internet?
Yeah, it's obviously all of us are searching for, there's no right answer. Again, let me quote the Alan Newell says, you need to have a secret weapon. You need to think about what a secret weapon is. So all of us have our own secret weapon, and being smart and working hard do not count, right? I do think that we all have different access. I was in Pittsburgh, I thought our secret weapon is not in Silicon Valley. Because why? Because in Silicon Valley, you also, at Berkeley, you have a tremendous secret weapon. You see tremendous of the industry. When we're at CMU, we're far away from the industry. Then you have to do a potential different style of work, pick a different style of work. And there's tremendous emphasis on collaboration when there. Maybe it's access to specific data set. For example, the ones that I happen to work with in the Conviva years, Conviva was a secret weapon for many of the collaborators, right? Because we have data set access nobody has, right? And we have our problems, we have a deep understanding of certain problem space nobody else has, right? So those are some of the examples. I also think in general, I think the first paper, you don't have to worry about the Turing Award yet. The key is take a piece of work, do a incremental better paper, because that helps you not only write the paper well, but also really understand what the problem formulation is. Because I think it's not the solution, it's really the deeply understanding the problem space that ultimately the best work. So at least that's my understanding.
Thank you, Professor Zhang, for your great talk. And I'm Junchen from UIUC, and I want to ask a question about the video industry has been developing very fast in the past few decades. So I'm wondering what's your insights about what the video industry will become like in the next decade?
Which industry?
Video industry.
Video industry. Well, it's, actually, now that I'm in it, there's a lot of different segments, right? One is entertainment, which is the business we're in. And, but also, video is a rich media. I still think it's the most engaging media. So I think it's getting more and more used. If you go to a Nike website, you will see video. If you look at today's most impactful society mover, sort of application, TikTok. TikTok is not, we think it's a video. We talk, YouTube short is the video, but actually it's the way how people interact now. It's a new communication media. In fact, it's a new political force, right? I think that the more and then you have Zoom, which is, I think that we started, when I was a student, we started, Van Jacobson and several other people, Steve McCann, they're trying to build collaboration tools, that time called VAT and VIC, multimedia conferences. But if you look at that, it didn't take off until you have some kind of a real event like a COVID. All of a sudden now we're used living in the Zoom world, right? And obviously there are other people have this vision, whether it's constant presence, right? I think the remote office, there are a lot of constant presence thing right now. You have a shared office among them, or some kind of virtual reality reach. Again, generated content, the meta world, but I'll stream at you. It's not necessarily video, right? So it's a streaming. I think all of them will continue to evolve. And again, sort of the ecosystem and the drivers need to be there for that one application to show up, like the conference, like Zoom. It took a pandemic before it went mainstream. So sometimes there's external events.
Thank you.
Hi, and thank you for the great talk. Very, very inspiring. I enjoyed it. You had a slide on follow passion, not fashion, right? And that resonates with me a lot. I've been thinking that way, but I feel like with the age of AI, it's becoming much more difficult, right?
With what?
With AI,
yes.
Right? So suddenly, like, all computer science is like overshadowed by AI, right?
Yes.
So we have these discussions with my students, right? Can we still follow our passion and not jump on the AI bandwagon and kind of like survive? Like, I don't know what you think about that. Like, is that still feasible?
I think so. I do think so. I went through another euphoria. I mean, I think that was before it was, I was in the part of the bubble, internet. It's not a bubble, it's really a revolution. And those people who were doing AI research, they were not part of the bubble. They invented the next big thing, right? I think as a system, we're much more closer, system community, we're much closer to any of the disciplines. I think that the foundational level, I think that even the basic in this community, right? So I think the mobile technologies, whether you think about drone, change the world, have some AI, but a lot of system components, right? Now we're talking about, I remember in the days that we talked about drone form a network, and then that time drone didn't exist yet. Now they're real. So I think that even the basic technology layer, right? The connectivity problem has not been solved. Everywhere I go, I still run into problems. I think that those, at the fundamental level, if there's a 10x better solution, again, it will change the world, right? If you think of this community, mobile, I take a mobile as example. We think about internet, but a biggest thing happened was the mobile internet. Nowadays, the net is all about phones, and that's a mobile device. And that's all the work done by this community contribute to that, right? So to enable that. Now, what is the next big leap? I think that, again, you really need to know, you need to have a deep understanding of the problem space. I really think that, because the conviction and the passion and interest is all rooted on the problem space, understanding. And I think that obviously AI, AI as a technology can help. First of all, it's a tool. The second, obviously, can this technology help certain AI use cases? But I think that at system level, there's some fundamental breakthroughs still need to be happen. I think independent is sort of on the separate dimensions from the AI. At least that's how I think about it. So I put a name there, a picture there. Many of you didn't see. It was on the first NASDAQ conference. It was Sandy Fraser. Sandy Fraser was again, late Sandy Fraser. He was a chief scientist of AT&T. He was a person who set up a network. I had a student have access to. The NSF backbone was T1, and it has a 45 megabits per second network. But he said something at that time, his labs invented, semiconductor, invented sort of Unix. And he always said, look, his methodologies avoid the hot topic. No, again, that's an extreme version. And he says, the first person go to the moon, bring a rock back, that's very valuable. The next set of rocks, they're okay. So I think the Andrew Barton, said something, look, he actually said a little bit lesser. He said, don't indifferent to fashion. Not saying avoid fashion. That's a stronger word. But definitely don't follow too much in fashion probably is good advice, because it's already too hot.
Let's thank the speaker again. Thank you so much.